and today we are going to explore the system design for a graph database which will be acting as a cloud service. So in general, there are a lot of tasks which are requiring the graph data itself. So we are looking for the social networks, recommendation engines, knowledge graphs, supply chain graphs, fraud detection, and many others. So, and the challenge here is the graphs is hard to scale. It's hard to build the relationships between the multiple nodes in the cluster. So, and of course, the issue is about the partitioning. So in case if we will have a lot of partitions of the same adjacency list, then we will have the problem how we are going to visit all of them. That's the issue. So let's take a look at our functional requirements. So they are about adding the new node to the graph. That means that we should add it for some parent and build the relationship between them. So and also I would like to say that we should try to find some node in the graph. That's also the interesting idea, and how we may do that through these things. So let's imagine that for simplicity we have just the one connected component inside our graph itself. We are going to connect all the vertices using the edges, and so let's skip the different scenarios and the stuff like that. So we may do some follow-up video about them. So, and in general, I will try to cover two cases. One of them is about like some quick solution, which will be based on the industry standards. And another one is about, some scientific way and exploring the systems like JTrain and A1. Okay, so let's check the non-functional requirements, and I would say that it could be great to have at least some consistency. I mean, the eventual consistency for these systems. We will think about some other options, how it could be possible. And so our queries should have low latency. So we should support fast traversals. So, and we should take care about the data locality. Okay, so, and in general, we will have, let's say that it's about like 100 million requests for adding the data and the same value for reading it. So, and let me try to calculate it like 100 million divide by 24 hours divide by 60 minutes and the 60 seconds. We will have, so let's try to say that we have this value of the request per second for add, and the same for a read. So not so huge, but still we should think how to deal with that efficiently. Okay, so we have these calculations. Let's say that it's our backend envelope calculations. So in general, let's skip the part with the storing the data and things like that. And so currently let's decide which way we will have some points for our API. Yeah, we have the two entry points. One of them is about, let's say, some add, yeah, like with the some parameter parent ID, some identifier, and uh, so we may customize the identifier, but let's say that it's a parent ID, and here in the body, yeah, body, we should add the child value, and this guy should return uh, like so the response 21 and some child ID or record ID. That's fine. So we have like this add thing which should be post, and we should also try to do the traverse and find some get, yeah, get, and that's about some find, and I would like to add here some like vertex ID. And return value. So like that. So in general we are fine here, and so as a next step I will move to the designing our service itself. And so I will try to explain a few things there before we will move on. So I will try to cover the following thing. That so my first approach is definitely will be based on some usage of the Neo4j database. Let me try to find it in my library. So I have some graph database there, and give me 1 second. So here is my GraphDB. I will call it Neo4j from a start. So, and I will use multiple instances of this database. Let me do that. So, and what I would like to add here, that this database is definitely about the single node graph database, which is using some kind of linked lists under the hood. So, and instead of storing data in the relational tables as popular relational database does, it stores the data as nodes and relationships between them. So, and core concepts for this database is about, some node under the hood and some, relationships. I'm about, some kind of lives in and some friend with. By the way, yeah, so I'm trying to add the syntax here because of it's really close or kind of a part of Kefir. That's the query language for the graph database. Yeah, so and of course node has a properties. This is like the metadata of the node. So, for example, both nodes and relationships can have attributes like the, for example, node Alice, age 30, and the stuff like that. And the label, like here we should have the properties and label. This is the type of the node type. For example, person or like movie or some connection and the stuff like that. So we have this Neo4j as a backend there, and so under the hood, Neo4j uses like both disk storage and in-memory caching. Each node and relationship has the unique identifier and the direct links to its neighbors. And when we are trying to traverse the graph, Neo4j simply follows those links without index lookups, making each traversal step by O1. So, and in general, it really close to some, exploring the double linked list. So, I mean the double linked list, yeah. So, it's just about, like moving from the different pointers from the first pointer to the next one, like that. uh, I mean the Neo4j internal structure is conceptually similar to the doubly linked list idea, and each node stores links to the neighbors, which allows really fast graph traversal, as I said before. So probably that's kind of all for Neo4j as a database for our future system. But I would like to add that in some newer versions, the distributed graph is possible to build for a Neo4j. Some installations like the Aura DS Neo4j Fabric, they are about some distributed setup. So, but in general, Neo4j just about one leader and additional replicas. Like popular database MongoDB for the documents or the relational databases. So the idea is kind of the same, but using the graph. We may explore DocumentDB later in the more details, but so I would like to stop here, and so I would like to move on to the our service itself. So that's our backend, and here we have the users, which are going to populate the data to some load balancer. So probably that should be some API gateway. Let me try to modify it like API gateway. So it will be used for rate limiting, some security things like managing the JWT tokens, OWASP, assigning some permissions for from the JWT for every user. So probably it may work with our like some additional mechanisms and things like that. So, and let's say that all of this, Neo4j instances in a cloud terminology, that's our data plane. And what about the control plane itself? And the control plane, I would like to propose you to design to the some really close manner as a CQRS architecture does. So I would like to skip currently Googling what is the CQRS but I will add the related thing to my LinkedIn post. So in general, I would like to add two types of the behavior here. So one of them will be our work coordinator. So I mean, sorry, right coordinator. Yeah. So it's our right coordinator. And so in general, this right coordinator could be a kind of complex part of our service because of it should do the next. So let's address the operations over there. So we should get, let's say, some hash from our node. Let's imagine that we are adding new node. Yeah. Mm, so hash from vertex. Uh, sorry. First of all, we should find the parent. Hash for a vertex, and add to the graph. Add to the graph to local node. By node, I mean the physical node of our Neo4j backend. Okay, so and here is the populating of the data. But you know that here is the trick, that we could lose the things over this over the any of these steps. This is the first problem, which could be, complex to solve, and it could be like complex to manage the things with that, and we should find a way how to manage the distributed transaction here. So it's kind of, you know, mm, kind of complex to do that, and how to coordinate the transaction between the two Neo4j nodes. Another problem is related to the hash, this vertex. So we will increase the complexity of our like finding of the any uh, any node by adding more more uh, relationships in a distributed environment. So we will completely lose the locality. And here we should play with some another algorithms which are about, some graph partitioning. You may Google around about it, and there are a lot of concepts how it's possible to deal with. It's kind of tricky, and so in general, I would like to highlight for you the some Metis uh, algorithm. So it's like about the locally aware partitioning. So in general, what it does, so it's about some minimizing the number of the edges cuts between shards while keeping shard sizes balanced. Let's imagine, let's go back, and let's imagine that, for example, the parent is here and the child will be here. So, and we will add another one guy here. And so it will be complex to manage all of these things through our reading flow because of this, hops between the nodes in our network uh, will increase the timing a lot. Okay, so and what is the idea of this Matisse algorithm? So uh, it's about some, you know, uh, let's say stitching of the graph. This is the first step. The second step is about, some initial partitioning. I mean, so the first step, we are going to stitch the vertices with the heavy edges when there are uh, a lot of nodes. I mean the other vertices in the adjacency list. So we will build some super vertices, and we are repeating until the graph will be like really small. So and after that we will partition. We will do the partitions by the k number. For example, using the greedy cut, or with some other algorithm for creating the partitions from some uh, like amount of data. And the step 3 is about uh, like unpacking of the graph. So and after that we may store this data to the local machines. So in general, what it does, it's just about, in case if we have the node, I mean, sorry, the vertex and adjacency list. So we will try to store it at least on the one machine. Or, in the worst scenario, it's about the same rack of the cluster. So that's the idea of this algorithm here. So, and I would like to say that so how it will work in general. So here we will prepare some micro batches like of the newer like vertices and edges. Uh, Build some temporary subgraph. So this, our graph partitioning algorithm will analyze the structure and outputs the like, let me add here like vertex ID to some shard ID, shard ID. So and we will store it to the our neo4j. So how we how it's possible, we will try to do that using some two-phase commit, but for this level I would like to avoid that here. And another option is about using sagas. It's about some eventual consistency, but what we will do in case if our coordinator which is working under this transaction will die? That's the question, and here I would like to add some new component. I will call it like our like recovery, like transaction transaction recovery coordinator, and this guy will work with the Redis. Well, give me a chance to find it. So this is the Redis. I mean that our right coordinator will send the data to the Redis. And so in general, we are storing the like our transaction plan there. And so as a next step, when transaction will die, this recovery coordinator by schedule is going to work with this Redis. And in case if something going wrong, we are going to reschedule the transaction execution for the right coordinator. So that means that we will have the real eventual consistency with a, let's call it, minimal complexity. That's kind of complex, and so I would like to try to add more things here. So would like to highlight the how the data will be stored. So that's our data structure under the like our Neo4j. So and about our uh, some sort of the transaction planning here, we should add some also data structure which will be about some transaction ID. So let me move the API here. Yeah, and this guy also here. Yeah, that could be better. So here we have the transaction ID, some state, uh, also, probably created that. Yeah. And steps. And they are about, like step 1, step ID. I mean, like operation create vertex or update ages age. And what else? Like vertex ID. So like some, shard reference. Shard ref. I'm going to add it for avoiding any recalculation of that. Some, also payload. It could be like the value which could be not added, and like the child ID, which we are adding child ID. It's also optional. So like that. So we are going to store the data to the Neo4j as a backend using the Saga. So like Saga. What is the Saga, by the way? So I won't stop currently on this here, but in general, that's another approach how to build the distributed transaction. You may Google around about Saga pattern for the microservices, and so you may take a look at all of the schemas, like how it's possible to build the transaction using the choreography, and for from time to time it's about building some orchestrators. So and I'm about the orchestration based Saga here, and our right coordinator will be this kind of guy who manage it. So let's summarize here. So we are going to use the Saga for distributed transactions, and we are going to use some, graph partitioning algorithm for avoiding uh, using hashing, just hashing for sending different data in the different nodes. Because of, for example, if parent is here and child is here, then it might be really complex to support the some fast queries. So that's our escape. And this guy is will work for O v multiply e complexity. Uh, so it's because of the DFS, which I mean the some traversal BFS or DFS, which we will use for like visiting the our graph. So kind of not really optimal, but still we are trying to do our best here using this approach. And so we know about the some problems with the complexity, with the applying. I'm not sure about the time complexity for for the uh, for algorithm graph partitioning. It's kind of also could be the some additional complexity, but here that could be definitely like let's let's have the worst scenario that it's v plus uh yeah like that. So in case if I say the multiply, that's the mistake, sorry. V plus e, like DFS complexity. And so that's probably it about our right coordinator. So, and let's try to move to the other entry, and I would like to call it as a read coordinator. And here is the trick that it's kind of complex to move through this also sync. And first of all, I would like to highlight that this BFS or DFS across charts involves many network round trips. That is why I would like to start from some caching layer. So in case if we will have some ORU cache, like cache here, for managing this syncs efficiently. So in case if we here we have the post, let me add it. Yeah, so here we are adding add flow, and here we have the get flow, like find, better to say, yeah, find flow. So, and first of all, we are going to try to get the all the data from the cache using the strategies that we have some you know like we uh we are trying to get the some vertex ID, and we are going to the cache and just get all of the syncs by O1 time. That's really efficient. But what we should do in case if we haven't this kind of syncs in the cache? So it's interesting question. We are moving to explore the data across all the our nodes. So like this, and this. It's kind of tricky and complex. So, and it's kind of painful because of it will take a lot of time. It still will be like O v plus e, like the our like distributed graph traversal. But here is the thing that we have the network between these hosts, and it will take a lot of time. So, and I would say that there is some solution, and this solution is called Pregel. That's about like parallel graph and Google. So, and the framework or some approach is based on the some Google idea how to do the uh, parallel queries across the graph. So this is first of all the parallelization and some lazy loading for the vertices across the things. So let me out here like Pregel. So the idea itself probably is really close to some ORM solutions such as, for example, Hibernate for Java or other similar technologies which are helping us to do the lazy loading for a data. For example, if my graph has like 900 of the items and all of them are connected to the some one, that's some vertex which has the big adjacency list. So we are going to move through all of the edges when we are just getting this point, and we are trying to you know to find this vertex. So we are starting exploring the graph, and we are when we explore it like some part of this loaded uh, piece of the uh, children list. So, for example, like 75%. Under the hood, we are starting the procedure for adding more data to the batch. So we just populating all of this to the cache asynchronously and reading from the cache to and provide our users. So of course, we are looking for some pages. And for example, in case if we scrolling some part of these pages, that's could be the signal for our read coordinator to start the Pregel procedure to move through the through the queries. So in general, read coordinator receives a query, find path from some X, start a Pregel like traversal, find the shard for vertex X, sends the subqueries to shards holding neighboring vertices, and each shard processes its local vertices in parallel. So, and this coordinator, so it helps us to merge partial results. So like some intermediate values will be cached using this cache. And so in general, we also, I forgot to add it. Yeah. So we should have some, visited Bloom filter, like some visited Bloom filter, which will help us like Bloom filter, which will help us to avoid the duplicates in the result. So that's kind of it. I would say that it's kind of complex, and so it's like not really trivial stuff there. And in general, I would say that so it's like good approach for proof of concepts, but it's bad from the multiple things. So kind of like Pregel here, it could be probably hard to add it as some adoption for Neo4j and to use it in a distributed way. So that's kind of first idea how to deal with that. Yeah. So and another option is uh, to to move through some scientific way. How we could do that? I will copy that part of the solution, like we still managing some nodes, but we will not have this Neo4j things. Yeah. Uh, so in general, we are still about the some functional requirements, which are about the same. So I would like to avoid copying these calculations. So let's maybe copy the our API. Yeah, here is our API. And so I would like to avoid copying the some data structures because of they are about some nodes, and here I forgot to add some generic thing like vertex ID to the some adjacency list. It's in the our cache, and for visited bloom filter, that's about just the vertexes IDs. So that's kind of it for the data structure here. Yeah. Okay. So in general, currently we are kind of fine with the our original idea with the like quick solution. Let me mark it like quick here. Yeah. Sorry, something wrong with the probably a lot of symbols. Yeah, but still that's the quick idea. And how to deal with that like faster. And so it's possible or not to do something in addition. And I would say that yes. Like we are going to continue. Let me try to remove it here and maybe add something wrong. So that's the quick solution still. But yeah, so let's move here and let's think how it could be in the databases like the GTrain or some others like databases, scientific projects. Yeah. So we are still about some API gateway, and so what we are doing here. So we are about masterless architecture, and it means that we haven't a global coordinator. Any node that receives the request becomes the local coordinator. So currently we have a nodes here, like one node, another. So let's assume that we have like 5 nodes here. Yeah. And let's have the example that we are just running the query from this node. So this gateway randomly find this node there, and so we are going to try the to be the local coordinator of our query. So we are still about the same approach for the like write flow. We are going to add the data using using the post, and so this local coordinator will work with other nodes to find the uh, related places where we should add the data. And what about the some transaction levels? So from the transaction levels point of view, that's could be interesting to do the things. Yeah. So uh, first of all, I would like to add that for this scientific system, what we could use some remote direct memory access. So I will post this approach to not the approach, but better to say the technology for the clusters to my LinkedIn post. And so what I would like to say here that this RDMA should have the some like additional physical layer. So it's pretty unsecure because of RDMA. It's just about working with the uh, network adapter of your computer and just directly input the data to your physical memory. I mean the RAM. So uh, this is about some high throughput, but it's completely unsecure. Uh, Still, it's kind of used in some scientific organizations, and that's like could be interesting to explore for you to check if this technology still exists and still use it in the different areas, but probably it used. So like all of these queries are about some RDMA, and so we are going to use so about the transactions here. It's about the two approaches. So first one is about trying to use the some sort of uh, you know let's call it optimistic locks. So we are just going to update our graph first of all, and after that we are going to like let me add here transactions. And so the first flow is about using some optimistic concurrency control. That's about the optimistic locking. And so like in general all our vertexes are about storing one additional field that's called version, and we will use some maybe hybrid logical clocks or Lamport clocks for version stamps to avoid wall clock drift and achieve some ordering. And so this is like the first idea, and it's about to be more flexible, and it gives us the flexibility for storing the data, though, and it avoids heavy operations. Another idea is about using two-phase commit. About two-phase commit, you may read here. It's about definitely strong consistency. And this is like a protocol when our node, which is acting as a local coordinator, it will do the same, like find the vertex where we should attach our new node. It tried to do the partitioning using the some algorithm. Maybe that's the Matisse, or maybe that's some other algorithm for graph partitioning, and do that efficiently. And so in general, that's about updating the node. uh, I mean updating the nodes using some strong synchronization way. Like currently we are doing this, this, and this. All of the operations are added in some like kind of wall, and also two-phase commit is about some strong transaction plan, so and some strong recovery mechanisms. I'm not trying to revisit the two-phase commit, at least for now. We may do that later, but still that's kind of complex thing. Yeah. And about the reading flow, so like this is add, let me also mark it add, and this is read. Like for we are finding the another coordinator for this flow, like read. It also acting as a part of this RDMA sync. So we are also read the data through RDMA, and probably also could be great to add some global cache. Let me find it. So we should have some distributed cache here, and any reading flow should check this cache first of all for the existing kind of sync, like kind of our data there. So that's probably in general it from my side. So I'm wondering if you enjoyed this video. So, and if we compare these two approaches, so the first one, Neo4j plus coordinators, are about some central coordinator from the architecture point of view, and this approach is about some masterless. So like about partitioning, they are kind of equal because of they are using this Metis library. So and but for this case it's like dynamic, and so any node may be the read or write coordinator. About the communication, so the first approach, so I mean here we are using like TCP, or TCP definitely for connecting to the Neo4j, and probably the connections between our like coordinator and this transaction recovery coordinator will be based on some RPC. I mean, it could be great if we will use some gRPC and protocol buffers. And for like our another idea, the scientific way, we are using RDMA. So about the write consistency, so the first approach, we are here, we are using the Saga, and this guy for adding the things will use the transactions about optimistic concurrency control, or about the or about the two-phase commit. For the storage, I forgot to add it, sorry. So the first approach is definitely the disk-based because of the Neo4j as a backend. And this approach will be used in memory. We may add some, some wall, I mean the write headlock, for avoiding any problems with our transactions as an idea, and some eventually population the data to the disk, but still that's currently not affecting us a lot, and let's think that it's just about in memory. And we are using the technique like some partition plus offset. It's like which way RDMA just populating the data. So we just trying to find the our region, like region for better to say partition, yeah. And we just add the new item by O1 to the memory itself, like using RDMA. For the first option, from the consistency point of view, it's eventual, but for this thing, it's about the strong consistency per transaction per partition. Uh, so for the graph traversal, the first one is about some Pregel-like asynchronous, and here we are using native Pregel. For the latency, so first approach is about like milliseconds, and this second approach is much faster. That's about the like microseconds. Yeah, like that. So uh, in general, the graph database, it's not about just one other database. It's like a distributed operation system for the relationships, and it's really complex to do that. For example, for the second scenario, it's like based on my exploring of the JTRAN and A1 documentation. And so, if you would like, I may do the follow-up for this video, and I may implement parts of the first one database, and maybe at some some period of time we will do something for the second approach, and I may share both the approaches on my GitHub, and you may contribute. So you may add your thoughts in the comments. And so for today, that's all. Thanks a lot for your attention, and see you later. Bye.